Hello, welcome to our next set of notes for mathematical reasoning. We're on the second part of section B, 7b. So we're going to be covering probabilities this time that are considered either or probabilities. So the biggest difference here is instead of like the and probabilities where we're trying to get multiple parts of an event or multiple events to happen a certain way, here we're only doing one event, but we have several different outcomes, several different events that could happen that would be good for this. You know, it's the difference between you're drawing two cards, you want an ace and a jack, versus you're drawing just one card now, but you'd be happy either way if you got a jack or an ace. Either option is good. So there's a lot of times with probabilities, it's hard to calculate the probability for the entire thing for all the different options at once. So we can break it down and look at the different parts of the option, different aspects. You know, when you're playing cards, you might be happy with a diamond or you might be happy with a jack. Either option would be good, or both. Both is fine too. So you have to look at those probabilities. You know, you might be rolling a die and you say, I'd be fine with a 2 or a 3. Either option would give me what I want. So this is pretty common. These are either or probabilities. It's when we're looking at one event with multiple desired possibilities. You know, we're looking at either one of those being good or both. Now, before we can get too far into finding those kind of probabilities, we have to talk about the difference between overlapping and non-overlapping. So, overlapping events are events that share at least one outcome. So I talked about, you know, be a jack and an ace, they would be overlapping because there's no jacks or aces. But when I talked about a jack that's a diamond, there's overlap because there's just the jack of diamond. There's one difference in both events. So overlapping events, they, you know, at least one outcome is included in both events, both different possibilities. If there are no outcomes that are shared, so nothing shared, then we call them non-overlapping events. So no outcomes that are shared. Also called mutually exclusive. I'll just say overlap and non-overlap. So before you can do these kind of problems, you have to decide, is this an overlapping situation or non-overlapping situation? It's going to affect a little bit the way you calculate it. There's a formula that's separate for each one. So let's say you draw a card from a deck of cards, and there's a club or a black card. Well, clubs are black cards. So there's definitely lots of overlap because every club would also be in the set of black cards. You know, there are some black cards that are not clubs, there's the spades. We're just looking for anything that have anything. Excuse me, sorry. We're looking for it to have any cards that are in both sets, and there are. So because clubs are black, this does have overlap. You roll 2 dice and you get a sum of 7 or a pair. So there are a few things that add up to 7 or a pair of numbers. Well, you know, things that add up to 7, there's a few of them. You have like 1 and 6, 6 and 1, you have 2 and 5, 5 and 2, you have 3 and 4, 4 and 3. But none of those are pairs. You know, pairs, you know, 1, 1, 2, 2, 3, 3, so on and so forth. None of those add up to 7. They all add up to even numbers. They're not going to add up to an odd by 7. So here this would be non-overlapping. You didn't have to list all the options. I just did because it's a good kind of quick way to show you that like none of these match any of these. There's no overlap. Nothing that's in both sets. Now if I'd done sum of 8, well then 4, 4 would have been add to 8, and it would have had overlap. But since we picked sum of 7, nothing that adds to 7 is also a pair. You flip 3 coins, and you get 2 heads or 2 tails. At first you might think, oh yeah, you can get 2 heads and you can get 2 tails, but you can't have an event that is both. So this is non-overlapping, because in order to be overlapping, you have to have one event that fits in both categories. And there's no event that has 2 heads and has 2 tails because we only have 3 coins. So, you know, head, head, plus tails, tails, you know, 4 coins. Now, if I was flipping 4 coins, yes, this could happen. But since we're only flipping 3 coins, it's not going to happen. There's not enough. You can't get both at the same time. So these would actually be mutually exclusive. They would be non-overlapping. A dealer deals you a diamond or a face card. So we're looking for a diamond or face card. This is definitely overlapping because there are a few face cards that are also diamonds, like the jack of diamonds, the queen of diamonds, and of course the king of diamonds. So all those are both diamonds and ace cards. So this is open. Okay, so when we go to do the problems, you have to start off figuring out, is this an overlap situation or a non-overlap situation? We'll start with the non-overlapping situations, a little bit easier to calculate, and then we'll show you what to do with it. Not the overlapping. We'll do non-overlapping first, then overlapping. So these ones in this section are non-overlapping. If two events cannot occur together, they're non-overlapping. For example, you flip a coin and it lands on heads or tails, but not both. You can't get heads, you get heads or you get tails. That's it. You flip one coin. For two non-overlapping events, A or B, we use the following formula. So this is the formula. To find the probability of this or this, and this is non-overlapping. Find the probability of the first one, probability of the second one, and you just add them together. So when you want to find the probability of or probabilities, you just add things together. We start with and, we multiply with or, you end up adding things together. You just find the probability of each part and add them up. So say I want to draw a card. I'm looking for a blackjack or a red card. I'm doing probability of blackjack or red. Well, first I'm going to have to find the probability of getting a black jack, which there's only two black jacks, because there's the jack of spades and the jack of clubs. So that means there's only two cards that would fit this category. So there's 2 out of my 52 cards. And then I'm doing the probability of getting a red. And again, remember, I'm only drawing one card. I'm saying I'm going to draw one card, and I don't care if the card is a black jack or a red card, because either way I'll get what I want. So I'm looking for one of those two. So if I find the probability of getting a black jack, if I find the probability of red, well, there's half the deck is red, so 26 cards are red out of 52. And then I'll just add those together, and that'll give me all the cards that are either black, jack, or red. And you could do this by just sitting there and saying, okay, count the 26 red cards. You add the jack of spades, the jack of clubs, you get 28 cards, which is how many there are. There are 28 out of 52 when you do the addition. It's just not always easy to break this up or to add it all up. Especially when we get to overlapping, it's easy to miscount. So by doing it separately like this, you can kind of make it a little less confusing sometimes, especially if you get like multiple. We'll see that at the bottom of the page you can have more than just 2 different probabilities. Okay. With these ones, you do want to wait to simplify till the end, because if you simplify right here, a lot of times you can make the adding harder because you don't have common denominators. So we'll add first and then simplify. Again, we're always going to look and see is there anything I can divide the top and bottom by. These both divide by 4, and you can make your calculator do this, so you don't have to do it by hand. I'm just doing it by hand right now because it's pretty straightforward, and you get 7/13. So 7 out of the 13 cards work. So that's the idea. So non-overlapping, you just find the probability of each option, and then add those together. I have to simplify a little bit. Roll 2 6-sided dice, get 2 evens, or a sum of 12. I'm looking for evens. Or, sorry, I said 12. I'm in 11. I don't know why I said 12. So, I'm doing the probability of getting even first. So, if I want 2 evens, this is one of those where you can sit there and go, man, it might not be easy to super count this really fast. You can do it fairly fast. You just do 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 8. Or you can think about how fact that there's 3 evens on each dice, right? 2, 4, 6. And multiply 2 dice together, and you get 9 good options. So there's actually 9 good options. For the total number of options, since you roll 2 6-sided dice, they have 6 sides, and there's 2 of them, so you just do 6 times 6, because 6 options for the first one, 6 options for the next one. This is that whole multiplication principle we talked about in 7a. And like I said, it's really powerful. This is a really good rule, this whole multiplication principle. I can just think about 6 sides of the dice, 6 sides of the dice, and I multiply those, and I see that when I put 2 dice together, I get 36 possible combinations. So that's my chances of getting even, and I'm going to add to that chances of getting a sum of 11. This one's actually really easy to count because there's only 2 ways. You can do 5 and 6 or 6 and 5. It doesn't matter, the order matters, so there's 2 different options, 2 ways to get that, and there's still out of 36 options because we're still rolling 2 dice. Again, we're rolling 2 6-sided dice and looking for 2 different outcomes from that, even or sum of 11. Those are 2 options, and that's what we're doing. So 9 plus 2 gives me 11. I get 36 on the bottom. And this one doesn't simplify, so that's it. There are 11 ways to do this. And you could count up. Again, you could sit there and count all the different options, but there's 36 total options, so it may be kind of a pain. Multiplication principle helps with that. And you can list all the evens, list all the sum of 11. Then you can list it all out. See, there's 11 options, non-overlapping. A lot of times it's easier to think about the different parts separately, try and do them separately instead of trying doing everything all at once. Bag contains 5 red, 3 blue, 6 white, 2 yellow, and 4 green marbles. You draw a red or green marble. So looking for red or green. So probability of getting a red or a green. Again, these are all either or, saying I'm doing one marble, drawing one marble. I'm looking for either red or green. I don't care which color, which of those two colors it is. It could be red or green. Either one would be good. And just look for one of those two colors, red or green. All right, so first I find a probability of red. Then I find a probability of green, and then I add them. That's the whole methodology. So red, there's 5 red. Here I have what? 5, 8, 14, 16, 20. So we've got 20 marbles total. So 5 out of 20 are red. Green, we have 4 out of 20 for green. Add those up. Get 5 plus 4 is 9 out of 20. And that's our answer. We can't simplify that because 9 doesn't divide by 2 or 20 doesn't divide by 3 or 9, so that's not simplifying, and that's the answer. So there's a 9 and 20, not quite 1/2, not quite 10 out of 20, but there's a 9 out of 20 chance of getting a red or green. And again, you could have just added those together. So there's 5 red, 4 green, there's 9 total out of 20. And that's okay. That's there's more than one way to do a lot of probability problems. But this OR probability is a great way to take something that's got multiple parts and break it up into separate parts. In fact, it still works, like I said, if you have more than 2 options. So there are times when maybe it's hard to do everything all at once, but you can just break it up into separate pieces. So here I have where they have 3 different events that they like. We want to find the probability of one of the 3 happening. So you just find the probability of all 3 of those and add them all together. So say you want to roll 2 dice, we're going to say 6-sided dice. We're going to sum of 2, sum of 3, or sum of 4. So find the probability of sum of 2, 3, or 4. So we're going to find the probability of getting a sum of 2, probability of getting a sum of 3, and the probability of getting a sum of 4. We're just going to add those together. To add the 2, there's only one option, because that's 1 and 1. That's the only way to do it. Because we're rolling 2 dice, again, 6 times 6 tells me there are 36 possible combinations when you roll 2 dice. So 36 is the bottom number. Here I want to add to 3, so that's either 1, 2, or 2, 1. Those are the only ways to work. So 2 options out of 36. To add to 4, we could have like 1 and 3, 3 and 1, 2 and 2, and that's it. Those are the only ways you can get a sum of 4. So there's 3 options out of 36 that work to add to 4. Again, you could simplify ahead of time, but then you'd have not the matching denominators, so we don't want to do that. We want to leave it like it is first. Add 1 plus 2 plus 3 gives us 6, and then simplify. You always want to add before you simplify. 6 out of 36, we'll divide both by 6 so you get 1 out of 6. So 1/6 of the answers are good. I just want to make sure you simplify. Okay, so non-overlapping is pretty straightforward. You're basically just finding the probability of each one and adding them together. That's what it is. There's no overlap here. There's nothing where there's an event or an outcome that is in multiple of these events. You can't get 2 dice to add to 2 and 2 dice to add to 3 at the same time. They have to add one number or the other. You can't do both. So that's non-overlapping. Now, it gets a little more difficult when we have overlapping. Because when we count overlapping, we have to worry about that overlap. So when 2 events share at least one outcome with all those overlapping, for example, you want to draw a queen or a spade from a deck of 52 cards. Since the queen of spades is both a queen and a spade, we can't do the odds like we were before. Because if you had the odds of getting a queen, the odds of getting a spade, you would count the queen of spades twice. And we don't want to count it twice because it's only one card. So when we do these ones, we have to do it a little differently. We're still going to find the probability of each part, but we're going to subtract the probability of getting the overlap. So this right here, this is the overlap. So the trick here is you say, okay, I'm going to find the probability of getting a queen, I'm going to find the probability of getting a spade. And so you got all the queens, all the spades, but again, like I said, you got queen of spades twice, because you got a queen of spades for queens, you got a queen of spades for spades. So what you do is you find out how many overlaps there are. In this case, it's just the one, the queen of spades, and you subtract that from the rest, and now you've got the probability without double counting that queen of spades. So that's the trick here. We don't want to count that queen of spades twice. So when we do this probability with overlapping, it's all about having this overlap. We have to subtract the overlap. It's not A and B like we're doing, two things. When we did and probabilities earlier, I'm drawing two cards trying to get queen and get a spade. No, this is probably of getting something that's both. It's both A and B. It's a queen of spades. Okay, so that's what this is saying here. It's not an and probability. We're not drawing two cards. We're just doing one probability. We're trying to find something in the probability, something that's in both. It's the overlap. So let's say you want to draw a card from the deck of 50 cards. You want to get a heart or a king. So you're probably trying to getting a heart. Just draw a heart because it's faster, or a king. So either way, you're happy. If you get a heart, you're happy. If you get a king, you're happy. So that's what we're looking for. So to do this one, we're going to find the probability of getting a heart plus the probability of getting a king. But we have to worry about the fact that there are some cards that are both, right? There's the king of hearts. It is both a heart and a king. So we need to subtract the probability of getting both. So I'm just going to put both. Something that is both a king and a heart. Okay, so there are 13 hearts out of a deck of 52 cards. There are 4 kings out of a deck of 52 cards. And there is only one that is both. This is the king of hearts. That's the only thing that works in both. Sometimes overlap will be bigger. This one is just one thing in the overlap, and it has a 1 out of 52 chance of being drawn. That's included in this 13, because one of these 13 cards is the heart king, the king of hearts, and one of these 4 cards, one of these 4 kings, is the king of hearts. So we've counted this king of hearts twice, once here, once here. We only counted the rest of the kings once. The king of spades, king of clubs, king of diamonds, they're included here, but they're not included here. The other hearts, 2, 3, 4, 5, 6, 7, 8, 10 of hearts, not jack, queen, all that, they're included here, but they're not included here because they're not kings. The only thing that got counted both was the king of hearts. So we're going to add these first two, we're going to subtract that overlap. By taking away this overlap, now we have an answer that includes all the cards once and doesn't include any of the cards twice. We don't want to include the king of hearts twice. So 13 plus 4, got 17 minus the king of hearts, so we get 16 because we're taking away that one that we counted twice out of 52, and then simplify. Divide top number by 4, so you get 4 over 13. Again, if you don't feel comfortable simplifying, you can make your calculator like I showed you earlier. Say you roll 2 6-sided dice, you want to get a sum of 8 or 2 evens. So I'm going to roll either a sum of 8 or evens. So first, I'm going to find the chances. What do I get? Or my chances of getting a sum of 8. Then I'm going to find my probability of getting evens. In this case, there's no overlap because 4 plus 4, those are evens that add up to 8. So there is overlap in this one. And I just gave you one example, but that's as long as there's something that works that's in both sets, then we have overlap. So we're going to find the probability of getting both. Things that add up to 8. So 2 and 6. You can't go with 1 because 1 plus 7 is 8, and we don't have the 7 on a 6-sided die. So we have 6 and 2. We have 3 and 5. We have 5 and 3, and we have 4 and 4. I think that's all of our options that add up to 8. So there's 1, 2, 3, 4, 5. 5 ways to add up to 8 out of the 36 possible combinations. Again, 6-sided dice. 6 times 6, there are 36 possible outcomes. Using that multiplication principle, 6 sided on the first die, 6 sided on the second die, there's 36 different outcomes you can get. Evens. So there's 3 evens on the first side, and there's 3 evens on the second side, so 2, 4, 6, 2, 4, 6. So there's actually 9 different ways to get evens. We actually did this one a little bit earlier today. So there's 9 out of 36 ways to get evens. 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, 6, 2, 6, 4, 6, 6. Those are the different evens. There's 9 of them. Probability of getting both. Well, 4, 4 is even, and 6, 2 and 2, 6 are evens. Those are the only ways that you can get both a sum of 8 and evens. 3, 5, 5, 3 don't work because they're not both evens. So there's 3 options that count as adding up to 8, because 2, 6, 6, 2, and 4, 4 add up to 8. But they also count in the both even set. So we're going to subtract those. From our previous options. So we add up the sum of 8 plus the evens, subtract the probability of getting both. There's only 3 options that are in both. So 5 plus 9, I get 14, minus 3 gives me 11 out of 36. There are 11 good options. Now I've only counted everything once. I've only counted 2, 6 once. I didn't count for both this and this because it took away the overlap. So again, I counted 2, 6 previously when I was adding these two, and before I did the overlap, I counted it twice because it was both some and even. The subtracting the both is basically just taking that stuff that got double counted and taking out a copy, so there's only one set left. So now we have counted everything once. We've included all the things that add to 8, we've included 3, 5, and 5, 3, we've included all the things that are even. We haven't counted anything too many times. That's the method. So overlap, you have to subtract the overlap. That's the big difference with overlap. Okay, so after you do overlap, then you have to start worrying about, okay, I'm not always going to tell you what kind of problems these are. So those ones so far I told you if they're overlap or not overlap. Now I can just give you a problem, and you have to figure out, is it overlapping, not overlapping? Then you can decide based on that which method you need to use and solve the answer. So for example, you draw a marble out of a bag with 2 white, 4 red, 3 blue, and 2 green marbles. What is the probability you draw green, blue, or red? Well, a marble can't be green and blue, right? Because there was some green, there was blue, there was red. It can't be both colors. There's nothing that's both. These 3 options have no overlap. And if there's no overlap, then this is non-overlapping. And we just find the probability by doing each one separately. So to find the probability of green, blue, or red, we just find each one by itself. And then add them up. The only difference is if there was overlap, I'd have to worry about subtracting at the end. In this case, there is no overlap. I'd be subtracting 0. That'd be silly. It'd be a waste of time. There's nothing that is both green and blue, or nothing that's both blue or red, nothing that's both green and red. It has to be one of these 3 colors. They're all solid color marbles. I'm just going to do these each by themselves, add them up, get my answer. Green marbles, there are 2. So 2, 6, 9, 11 marbles. So 2 out of 11 are green. The blue marbles, there are 3 blue, so 3 out of 11. And red marbles, there are 4 red out of 11. So 2, 5, and 9. 4 is 9, so 9 out of 11 is the answer. Okay, you draw 1 card from a deck of 52 cards, whoops, typo, and you draw an even number or a red card. Whatever, even number or a red card. Even numbers, 2, 4, 6, 8, 10. I wouldn't worry about face cards, those are numbers. 2, 4, 6, 8, 10. Could also be red cards, right? Because you have the 2 of hearts, 2 of diamonds, 2 of 2 of hearts, 2 diamonds, or 4 of hearts, 4 diamonds, 6 of hearts, 6 diamonds. There is definitely overlap. So even reds. So to do this one, we're going to find the probability of each one. We'll find the probability of getting even, and the probability of getting red, but we're going to have to subtract the overlap. That's the only difference. When there's overlap, after you do the addition part, find the probability of each one and add them, you have to subtract the probability of getting both, something that's in both sets. Evens, so it's 2, 4, 6, 8, 10, that's 5 evens for 4 different suits, right? 2, 4, 6, 8, 10 of hearts, 2, 4, 6, 8, 10 of diamonds, spades, clubs. So there are 20 evens. Count all the 2, 4, 6, 8, 10s of hearts, diamonds, spades, and clubs. You get 20 cards out of the 52 cards. Reds, there are actually 26 reds, because again, half the deck is red, the other half is black. And both, how many things are both? Well, there's actually 10 that are both. The 2, 4, 6, 8 of hearts and diamonds. So there's, I forgot 10. 2, 4, 6, 8, 10. There's 5 hearts and 5 diamonds that are both, and that's our overlap. So again, we're going to add together the probability of getting red, probably getting even, even red, and then we're going to subtract probably getting something that's in both sets. So you get 46 minus 10, I get 36, 52. It does simplify, you can divide by 4, and you get 9 out of 13. And that's the answer though. 9 out of 13. You need to simplify this. There you go. So non-overlapping, overlapping. Big difference is if there's overlap, you have to do the subtraction step. If it's not overlapping, you don't have to worry about subtracting anything because there's nothing to subtract. Last page I throw in here, this is just, when you get to the test, you're going to have problems that are OR probabilities, and you're going to have problems that are AND probabilities, and they're going to be all mixed together on the test. So part of your job doing the test will be solving problems, but figure out which one they are. Are they an OR probability, or are they an AND probability? And then doing the appropriate probability then. So for the following examples, let's use AND or OR probability, solve them. We got to figure out what they are. So you're playing a dice game and you win if you roll a pair, or if you roll numbers that add up to 7. If your first die lands on 4, what is probably you will win. So at first you might think, oh, doing 2 dice. So this is an AND probability. But then you look closer, you realize actually we have options here. We could roll a pair, or we can roll a 7, and either option works for us. In fact, they even gave us what the first number is. So we're really just looking at the second dice. We're not even looking at 2 dice. So at first it might look like an AND, but it's definitely an OR. You can see right here, this is an OR probability. And this is a non-overlapping, because we're looking for a pair. Roll numbers that add up to 7. So if I already have a 4, then my other options are going to either be a 4 for my pair, or a 3, because that will add up to 7. So I'm really saying, what's the probability of getting a 4 or a 3? Because those are the 2 options that work, getting a pair or add to 7. Because there's no overlap, you can't get both a 4 and a 3. They're only rolling 1 die, so that's why. Because I already rolled their first die. Then there's no overlap, we just find the probability of each one. So what's the probability of my 4? What's the probability of my 3? And add them up. Since we're rolling, normal dice, 6-sided dice, I'm assuming they didn't say I should put that on there. We'll have 1 out of 6 that works. There's 1 4 side. There's 1 out of 6 that works. There's a 1 3 side. Just add them up, get 2 out of 6, and we'd simplify. So our answer would be 1/3. That's our answer for this one. But that's the idea. So you have to identify first off. You have to look at the question. You have to stop, think. Okay, like is this an AND or an OR? It can be misleading. Like we started off and it's like, wait, there's 2 dice. You're rolling 2 dice, but you already know what's going on with the first one. And really, we're looking at 2 different options. We're saying, hey, do I want to get this or do I want to get that? That's where it really comes up. Let's try one more. You're playing a roulette game where you could win if your next 2 spins are red. If there's a chance, 30% chance of spinning red ones, probably will win. Okay, so you notice that we now need 2 things to come out a certain way. That's where this comes into play. So your next 2 spins, this makes this an AND probability. I want this one to be a win, and then the next one to be a win. I want them both to be red. So AND probability is all about having 2 different things happen, and they both have to come out a certain way. I'm doing 2 spins, and they both have to come out certain ways. That's why this is an AND probability. This is definitely independent, because spinning a roulette wheel, the roulette wheel does not change chances. So it doesn't matter what I got on this spin, I'm not going to change the next spin. So since the chances don't change, it's independent, we're just going to find the probability of the first one being red, and find the probability of being the second one being red. Remember, with independent, and multiplication, we just find the probability of the first one red, and the probability of the second one red, and we just multiply. No given here because we're not changing probabilities. It's not dependent, it's independent. First chance, we have 30% chance of 0.30. Second one, still 30% chance. Chances don't change from roll to spin to spin. So we get 0.30 times 0.30, which I think is 0.09, but I'll double check. 0.30 times 0.30. Yeah, I get 0.09. So 0.09 or 9%. I'm not really picky about which way. If you want to leave it decimal or percent, that's both correct. They're the same as far as I'm concerned. You don't have to have fractions with probabilities. Notice this time I gave you decimals, so that's fine. You can turn them into fractions if you want. 30 over 100, that's fine. But you don't need to. It's fine to work in decimals. That's the nice thing about these rules, is you don't have to have all the counts. I don't know how many sides on this roulette wheel there are. But as soon as I know the probability, I can do things like multiply to find the probability of doing the same thing twice. You get red and red, and just multiply those things together. Okay, that's it for 7b part 2. It's a little bit shorter section, partially because we broke 7b into 2 sections, kind of taking our time on 7b so that we can cover both and or probabilities in a little more depth, a little more time. So again, the biggest thing here, and the thing that I get a lot of people missing on the test is when you're doing an either or probability, the either or, you're saying, I'm only doing one thing, I have multiple good options. Versus the and probabilities we did last time, when you use and probability, you're saying, I need two things to come out a certain way. This has to happen and this has to happen. You're doing multiple events. That's a big difference between the two. Okay, that's it for this section. We'll see you on the next one.